Welcome to our final lecture in this series of our Introduction to Structural Equation Modeling. In this class, you've learned a lot across this time, and in this lecture, you're going to learn about latent growth curve modeling. This piece is probably the most different of any of the SEM models you've done so far, and how it's run and how it's interpreted. Today is really meant to be an introduction to latent growth curve modeling, because it would really take a few lectures to truly cover it into depth, which we just simply don't have time for, and the other pieces tend to be more important for you to be able to understand how to run and interpret structural equation models. So on to latent growth curve modeling. Latent growth curve modeling is really a class of models, so it's a class within SEM for assessing longitudinal data where you're really assessing three things. The first thing is the starting point, or the intercept. So where people are at the beginning of a process. For example, you may be looking at the transition to parenthood. So you're really interested at that starting place of when the baby is born for first-time parents. Or you may be interested in marital happiness across time, so you're interested in a starting point of when that relationship begins. Or you may be looking at clinical data. So your starting point may be the starting point of therapy, session number 1. Where is their depression or anxiety levels at the beginning of therapy? And you want to assess trajectory across time for how depression levels or anxiety levels change across the course of therapy. And then trajectory of slope is that change. What is the directionality of it? Does it go up? Does it go down? How severe does it go up or down? Or in some cases, is it curvilinear? And in latent growth curve modeling, even though we're not going to cover it today, you can assess curvilinear trajectories across time as well. The third piece then is once we assess that intercept and that slope, and we can test that and see that it does work, and that we do see trajectories across time, what we are most interested in is what accounts for changes in those slopes and those starting points. So in that third piece, we're looking at predictors of the starting point and trajectory. So what accounts for different starting points in depression levels at therapy? What accounts for differences in trajectory across time? What makes that depression go further up or further down across time as we move through therapy? What is it the therapist can do that can actually help decrease that depression level more quickly? This is what we are doing in latent growth curve modeling. When you're doing a latent growth curve model, there are a few things it does require. Number one, you need at least 3 time points. So that means you need 3 different points in times minimum in order to do this. Typically, you'd want more than 3 point in times, but 3 time points is appropriate. Second thing that you need is you need scores that have the same units across time, can be said to measure the same construct at each assessment, and are not standardized. So you need unstandardized measures that are measured the exact same way at each time point. And then the third piece is you need data that are time structured, which means all the cases are assessed at the same intervals. So 3 things, you need at least 3 intervals. You need everybody to be tested at those intervals, and you need the measure to be the exact same at each of those time points. One benefit of latent growth curve modeling is those time points do not need to be equidistant. So in other words, those intervals can be different. You can have intervals at 1, 3, 9, and 24 months. You can have intervals at 1 year and 4 years and 12 years, as long as everybody is measured at each of those time points. Latent growth curve modeling offers quite a few benefits over traditional methods of ANOVA and regression. First, latent growth curve modeling is really considered by many to be the most powerful, informative, and innovative approach to the analysis of longitudinal data. You're seeing many more researchers use latent growth curve modeling over traditional approaches, especially as more are trained in and understand how to run latent growth curve models. Another benefit of this is that it enables researchers to test for differences in developmental trajectories across time. So we can actually look at different trajectories, not just a single one, and also look at those differences in those trajectories across time. We can distinguish group effects observed in means from individual effects. ANOVA cannot do this. It cannot assess and distinguish individual from group, but in this we can. And essentially the correlations will tell us the group effects and the covariances will tell us the individual effects when we're looking at the results section. And we can also distinguish between observed and unobserved variables. And this becomes very important because our starting point, our initial value, or our intercept becomes a latent variable, as well as our slope is a latent variable. And because of this, we can actually model and estimate measurement error, which traditional models cannot do. There are also additional advantages that are specific over ANOVA that really make latent growth curve analysis the replacement for ANOVA, especially repeated measures ANOVA and MANOVAs. The main thing is that we have the ability to measure model error covariances. And that's the main piece that you've heard me kind of distinguish throughout this course that distinguishes SEM from traditional statistical techniques. More specifically, ANOVA assumes that error variances of repeated measured variables are equal and independent. We don't have that assumption in latent growth curve modeling. Those error variances can be unequal and also can be dependent when we are working in latent growth curve analysis. Additionally, MANOVA does not assume independent errors. It assumes that those errors are dependent on each other. If you remember, that was a big piece when we looked at covariances using ANOVAs and MANOVAs. But neither ANOVA nor MANOVA directly analyze means of latent variables. We can do that. The third piece here is both of these traditional techniques also treat individual differences in growth trajectories as error variances. And that is actually a less accurate way to measure error and model error variances. It's much more accurate to do it in the way that SEM does it. So traditional statistics in ANOVA and MANOVA are incapable of capturing individual differences in trajectories across time, and also because of this, traditional statistics are becoming perceived as somewhat inadequate in that they prevent researchers from really seeking answers to interesting and important questions bearing on individual differences. So as we move forward in the field, and as you want to be, as I hope you are part of this movement forward in doing better analyses, more accurate analyses, and asking questions that help to advance the field. And as you move to do this, latent growth curve modeling becomes an important piece to advancing our field and our analyses and our research studies. And with that, the types of research questions that we can ask are really kind of any research question that bears on trajectory or change across time or starting points. But most especially those that ask about trajectory are the ones that really bear most on latent growth curve modeling. I have some examples here from actual studies of latent growth curve modeling research questions. The first one is from the Burton book. So, is there a difference in the rate of change in one's perceived body image for breast cancer patients who have undergone lumpectomy as opposed to mastectomy surgery? So we can actually look at changes across time and how people view themselves. The second one here is from another study. This is from an MFT published research study. The third one is an MFT published research study. So the second one, boys with increasing aggression, so child onset subtype, would show higher levels of concentration problems and peer rejection relative to non-aggressive boys at entrance to first grade. The second one is really looking at multiple groups or differences in groups of trajectory across time, which is an extension of latent growth curve modeling. The third example here is from alcohol substance abuse, and this is from a colleague of mine at Texas, who is now at Texas Tech. And her question here is the number of friends using alcohol in adolescence significantly related to the trajectory of binge drinking from adolescence to early adulthood? So what she was really looking at here is how many peers you have that also use alcohol. How does that impact the trajectory of binge drinking as adolescents move into early adulthood? In this same study, she also asked, is family cohesion in adolescence significantly related to a trajectory of binge drinking from adolescence to early adulthood? So in this study, she looked at that trajectory of binge drinking from adolescence into early adulthood, so that moving across time, and then her predictors that she was looking at was family cohesion and total number of friends who also use alcohol. So in this study, and this is I have this study in the example readings you can look at, and you can look at the results here of what she found with how family cohesion and peers influence trajectories of alcohol binge drinking for adolescents as they move into adulthood. When we are testing latent growth curve modelings, there are two really important factors we're looking at. You've heard me talk about these already. That's the initial status, or the slope, and the linear change, the initial status, which is the intercept, and the linear change, which is the slope. So the initial status, or the intercept, is that starting value, and the slope, or the linear change, is that change across time. Where do people move? What does that look like as they move across time for this dependent variable? The initial status and the linear change factors are specified to covary, so that means we have a with statement between the initial status, or the slope, or the intercept, and the linear change, or the slope, that we're always going to have a with statement there to make sure that we are correlating them to make sure that they are covarying together. When we do this, the mean of the initial status factor is the average initial level on whatever characteristic is measured over time. So for example, binge drinking. And the mean of the linear change reflects the average amount of linear change over time, adjusted for both of these being adjusted for measurement error. So the initial status is the average level, and the linear change is the average change across time. The variances, when we were looking at latent growth curve models, we're really interested in the variances in the results section. The variance of these factors reflect the degree of individual differences in, respectively, the average initial level and the rate of linear change. So the variance, remember that's the spread of the scores, the variance is going to tell us about individual differences for both the initial status and the linear change. The last piece here is that it is possible to measure the error covariance structure by specifying a pattern of correlated errors. So how we correlate those error covariances, like we correlate the initial status of latent variables, we're able to model the error covariance. So essentially what we're doing here is the initial status is going to give us the average, or the average initial level for those in our sample, and the linear change will give us the average change at each time period. And then the variances, it is going to help us understand the individual differences within our sample. So when we are conducting a latent growth curve model, we're going to do this in two steps. First, we're just going to test the latent growth curve model as is with no predictors. This is important to make sure that we can actually get good model fit and that it actually works as a model. Second, once we see that that model works well, we're then going to add predictors. So we're going to add variables to predict that. Like in the example of binge drinking, you first assess, can we actually model binge drinking across time, that trajectory across time. And then once we see that that fits, then we will add in our predictors of family cohesion and friends who also use alcohol. And I'm going to show you an example here over these next few slides of what the model looks like pictorially, and then also how you write out the syntax for a latent growth curve model. So here is step one. In this example, we have initial status here. This is the latent factor for your intercept, and then linear change, and this is your factor for your slope or trajectory across time. And then we have a variable here, year 1, year 2, year 3, year 4. This could be, in this example, it's kind of a blank slate. So this could be binge drinking at year 1, year 2, year 3, and year 4. It could be relationship status, depression, whatever our dependent variable is here. So what you will see here is the first thing that we do when we are modeling this is we actually do a lot of put a lot of constraints on our model. So you can see for the initial status, we constrain each of those factor loadings to be 1. So we set them all to be 1 because the initial status is the beginning. So the initial status is 1 as we for each of those. And then the linear change, we actually constrain that to be our time points starting with 0. So time 1 is 0, time 2 is 1, time 3 is 2, and time 3 is, time 1 is 0, time 2 is 1, time 3 is 2, time 4 is 3. So we just go 0, 1, 2, 3. or 0, 1, 2, 4, whatever that may be that can best represent the time factors that we have. In the Burn book, you may have seen an example where it was 0, 1, and then 2.33, and they had chosen to do that in that study because there was an equal distance between time 1 and time 2, and then a little bit longer time between time 2 and 3, and so they reflected that in the value there. But what you're doing is for your initial status, setting everything to 1, and for your linear change, you're going 0, 1, 2, 3, 4, 5, however many time points that you have. You'll notice in here also your measures at each time point. So your 1, your 2, your 3, your 4, those are your dependent variables. Those are the variables that are measured the same way at each time point. You'll notice this little triangle at the top. You haven't seen these in anything that I've done, but this is just a symbol that is not very well commonly used, but in the example I'm giving you here today, it's in here, so I wanted to explain this to you. This just simply means that mean structures are included in this analysis. In M+, mean structures are automatically included, so you don't need to do anything different in order to have that done in your model. But you can just, anywhere in these examples where you see that little triangle and arrows, you can just ignore that in these models. So this is then how you'd write out the model syntax when you are doing growth curve analysis. So you can see here we have initial status, and we're going to use the word by because we're doing a latent factor here. By year 1, year 2, year 3, and year 4. And then we're going to do the same thing with linear change. Linear change by year 1, year 2, year 3, year 4. But then we need to set these, constrain them to be equal for the initial status, everything to be 1. And for the linear change to go 0, 1, 2, 3. And so to do that, you just simply do an at symbol. So you do year 1 at 1, year 2 at 1, year 3 at 1, year 4 at 1 for the initial status, and then 0, 1, 2, 3, year 1 at 0, year 2 at 1, year 3 at 2, year 4 at 3. And we want to do our with statement, so our initial structure or initial status with linear change. That's the third line of the syntax there. So you can see here, first line, we're setting our initial status to 1. Second line, we're setting our time points, 0, 1, 2, and 3. Our third syntax here is giving our with statements of our initial status with linear change. This piece here is not necessary. M+ will automatically do it. I like to have it in here just to make me feel better when I do it, but this is the default in M+, so it isn't necessary to do. These last two lines, the fourth and the fifth line of the syntax, are important in order to meet the standards necessary in order to run a latent growth curve model. So the first piece here, that fourth line, that where you can see in brackets, you'll have seen this in brackets before when we, this is about setting means. When we are doing latent growth curve modeling, because we're looking at means with a lot of what we're doing, anything you do with means is in brackets. So this first one, where you see year 1 at 0, year 2 at 0, year 3 at 0, year 4 at 0, this is a specification that's necessary that sets the intercepts of these variables to 0. So this is just a necessary default setting when you're running a latent growth curve modeling. So you'll always include in brackets each of these set to 0, each of your models set to 0, so they're intercepts of this. The last one there then, you can just put both of your latent variables together in brackets, and this just is a specification that tells M+ that these serve as a set of parameters in the model. So when you're doing step 1, you'll always add in this fourth and fifth line, just in order to make sure that you're meeting the requirements necessary to run a latent growth curve model. The first 3 lines are really setting up the model. So when you run that first step, and if you run it and you have good model fit, you're then ready to move on to the second step. And in the second step, we're going to regress other variables onto our model when we're doing this. So here we go, moving into step 2. So step 2, you can see we have our syntax just like we had before. So we had our initial status by year 1, year 2, year 3, all set to 1. Our latent growth curve, set at year 1, 0, 1, 2, 3. Our initial status with our linear change across time, and then our fourth, fifth lines that work with the means to set the intercepts to 0, and to include those two. Make sure you're telling M+ that you're including those as measures in your model. And then what you can do is add in your predictors. So in this case, we're adding in gender and family status as predictors into our model. So you just write this syntax out as you've learned in our class all throughout this semester. So that's those last two lines on the left there. So we have our initial status on gender and family status. So we're loading gender and family status onto initial status, and then our linear change onto that as well. So you can see we have then added in those two factors as predictors into initial status and linear change. One last thing that we're going to add into here as well, if you remember back at the beginning of the semester, I said that there are a lot of major commands. So major commands are those commands like variables and output and model, you know, the ones that are in blue that you do with a colon. Those are your major commands. At the beginning of the semester, way back in that, I think it was the second lecture, I talked about some others that you use, but we're not going to use a lot this semester. Now we're going to use one of those other ones, and that's the plot command. So plot command gives you a graph, a plot of your results. For the most part, we don't need those in anything else that we're doing. However, when we're doing latent growth curve modeling, one of the primary ways that we display and report our results is through a graph, so that we can actually show what that linear change looks like at each time point. So the way you do this is just do plot, colon, and then the plot that we most commonly use is plot 1. There are many different types of plots you can do. There's plot 1, 2, 3, 4, and you can keep going. Plot 1 is what we're going to do. So we're going to say type equals plot 1, semicolon. So we're telling M+, we're going to use type 1 plot. That's what we're going to use. And then you just do series is. So the series works just like it does in Excel when you're creating plots and graphs. And it's just going to be year 1, 2, 3, and 4. So those are going to be your, year 1, 2, and 3. I'm following the same example we had from above, but you'd put in your manifest variables, your loadings onto your initial status and your latent variables across a series, and then in parentheses you're going to do LC. So that's your latent, your linear change. So we want to make sure that what this is telling M+ to do is create a plot, use my manifest variables that I have there, and plot those using the linear change. And then in the top right here, I have an example of what this could look like. In this one, we had 5 time points, so 0, 1, 2, and 3, and 4. And then we have the outcome measure, those levels. And then you can see the trajectories across time for the variety of participants we have and the variety of trajectories that we have in this specific data set. Next, I'm going to talk about reporting results. Reporting results is a bit different in latent growth curve analyses. If you decide to do latent growth curve analyses, you'll want to learn more about this and read more about this and look at more examples. But I do have an example reading here to kind of show you what these results look like. When you're reporting results, you're not going to be reporting the typical regression results, at least for the linear change and the initial status. For predictor variables, you'll do that. But for those two, if you remember, we set everything to be equal to 1 for the initial status, and then for the linear change, 0, 1, 2, 3. So your beta weights, those path coefficients that we normally look at, are set to those values. So they're not going to be of any use for us in actually reporting results. What we do look at, though, are the means, the standard errors of the intercept and the slope, and the variances. Because remember, the variances are really going to help us to understand the individual differences. And then we're going to use that plot and describe our plot, the one I showed you on the last slide, in our findings. So now we're going to look at an example of actually reporting results. I'm going to pull in some of the tables that you would see and some of the information and show you how you would write this up and how you would interpret it. So in this example here, we're looking at just the step 1 piece, so we're going to keep it simple in this example. And we have marital quality at time 1, time 2, and time 3, and we're looking at the intercept and slope across time. So in our model, we have our intercept set at 1 and our slope set at 0, 1, 2, 0, 1, and 2 for our 3 time points. So let's pretend we run that model, and then when we look at it, for the intercept and slope, we see the following estimates. And if you remember, the estimate is going to be the mean of our intercept and our mean of our slope. This SE is the standard error, and then the estimate over the SE is your t-value, and then we have the p-value. So in this one, what we would see is the mean slope for, in this example we're looking at all husbands here, but our mean slope for the rate of marital change across time, or in other words, their average marital trajectory is negative 0.56. So in other words, at each time point, the average score for their marital satisfaction decreases by 0.56 from that starting value of 22.73. So the negative value means on average, marital quality is declining, and this rate of marital decline is significantly steeper than no change at all. So that's what the p-value is telling you, is that slope is significantly different from zero. So it has a significant slope to it. Its steepness is significant. The units of change in this example are 2 years intervals. So time 1 is at year 0, time 2 is at 2 years, time 3 is then at 4 years. So what we can see is that every 2 years, on average, their marital quality declines by 0.56 units for the duration of this 4-year study. And then when we look at the with statement, so that correlation between the intercept and slope, if we saw, for example, it was negative 0.15, with a p-value of 0.779, what this would say is that there's no evidence that the initial level of their marital quality was related to the rate of change. So that relationship is just saying, like, looking at it and saying, like, is the rate of change related to that starting value? So, for example, if it was related, you may see that, like, people that start higher have a steeper decline. Those that start lower don't have as much of a steep decline. That would be if we saw that there was a relationship. But in this example here, we see that there's no relationship between the starting value and the rate of change. And now let's look at the next section. So one of the most important things that we look at in latent growth curve analyses are the variances. And in your results, you'll see the variances for your intercept and your slope, and then the residual variances. This is the error, the error terms for each of our manifest variables. We want to know if there is significant variation in the intercept and slope that we can explain with predictors. What we want to see is a significant amount, and we want to see that perhaps if we have significant predictors, if that significantly is associated with our slope, because that can help us to better understand those individual differences, what accounts for those differences. Many researchers do say that if there's not a significant variance here, then there's not really any point to move on to step 2 and adding predictor variables, because there's no significant variance to try and account for. However, other researchers still go on to this step, to step 2, even if the slope isn't significant, to see if there are some significant associations, at least with average change across time. And it may also be important, and some researchers don't really look at this, and it may be important to actually see what accounts for individual differences for the intercept. So in this example here, we see the intercept is significant. So there is a significant difference for where people start at. And our predictor variables may help us to account, and that may be an important research question to try and account for why is it people end up at where they do at the start. So why are some people happier at the beginning of marriage versus unhappy? Why do some people have greater levels of depression at the start of therapy versus other people? What are some things that account for that? That may be an important research question that you want to still move on to step 2 for. So in this example, I highlighted it here for you in this slide, where it shows you what I'm looking at for that rate of change. So what does the slope look like? What is the p-value for that? So this is the brief introduction to latent growth curve modeling, how you run it, how you interpret the results, how you create plots for this. The last section I'm going to cover here in this lecture are other important extensions of latent growth curve modeling that build on this, and I'm really just going to be introducing you to these pieces here. If we had a third lecture series, I'd go on to actually talk about these extensions in much more detail. So first off, we have time variant versus time varying. So when you're thinking about your predictors, there are 2 categories of predictors. There are time variant predictors, which are predictors that do not change across the course of the study. So in this case, it may be hair color, for example, that may not change across the course of the study. Family status, that if we were looking at a sample of participants where the family status remains the same across time for each participant. Gender is another example where we may look at a group where gender does not change across the course of this study for each participant. Time-varying predictors are predictors that do change across time. So behaviors, mental health status. If you're looking at, if you're doing like transgender research, you may actually, gender in this case may be a time-varying predictor where gender is changing. Gender identification is changing across time. So predictors, they can be time-variant or time-varying. Predictors can also be manifest, or they can also be latent variables themselves. So you can have predictors that are latent variables predicting the initial status and the linear change, so that you have a full structural equation modeling. One other extension is piecewise trajectory. So piecewise trajectory really happens when you see some really sharp changes in the trajectory. This is an indication that in fact you don't have one slope, but you have two or more slopes. So piecewise is really when you're actually looking at those multiple slopes here. So the example I have here, you can see how there is that distinct L bend in the growth curve in those linear change, where you have one linear change that goes across time, time points 0, 1, and 2, which is really time 1, 2, and 3. And then there is a second distinct shift that moves from 2, 3 to 4. So when you're doing this, you can actually, in your syntax, model out two distinct slopes. So on the right-hand side here, I have the pictorial view and then also the shorthand version of the syntax. So in this, you would have your initial status, but then you have slope 1 and slope 2. And when you're doing this, you'll notice in the syntax for slope 1, for that slope, we have it as 0, 1, 2, and then it stays at 2 for 3 and 4, because we are just predicting the slope, that slope 1 is just for time points 0, 1, and 2. And then for the second slope, you can see that we have set those time points to 0, 0, 0, 1, 2, so that point 2 here is set for 0 for slope 2, because that's really the starting point for slope 2. Then we go 0, 1, 2. So when you're doing a piecewise trajectory, for that first slope, you're going to go 0, 1, and then wherever that slope stops, you're going to keep it that same value. So in this case, 0, 1, 2, and then you're going to keep it at 2 for the 3 and 4. And then for your second slope, you're going to have it be at 0 until your starting point for that second slope. So that's why for 0, 1, and 2, we have it set for 0 for year 1, year 2, and year 3. And then year 4 and 5 is where it really starts, so that's where we have 1 and 2. So this will give us those two separate slopes to give us a piecewise model. The last piece I want to very briefly introduce you to is growth mixture modeling. Growth mixture modeling is really the very edge of what we are doing in the field right now with latent growth curve modeling. What growth mixture modeling does is really look at individual groups, or in this case what they call classes, of people that are in those trajectories. The most famous example of this was done by Jared Durkee. There is a very classic model of marital satisfaction across time where we can see these pretty predictable slopes where, this is actually a piecewise slope, that marital satisfaction may, or actually no, yeah, it is a little piecewise, where marital satisfaction starts high and slowly decreases across time until the children leave the house, and then it can increase across time. So we can kind of see that curve, and this is a pretty famous study that was done 20, 30 years ago about marital satisfaction. Then Jared Durkee comes along and does a growth mixture model. Growth mixture model looks at that intercept, so that starting place, the slope across time, and then it looks at individual groups within that. So what Jared Durkee had found is that there are actually 4 different groups that we can actually see with that. There's a group that has a really sharp decline, so they start high and they just drop off the face of the planet, and they never recover. It stays low. We can see a second group where there's actually an increase across time, where their marital satisfaction actually gets better across time. We can see a third group that starts kind of steady and then slowly starts to decline, that kind of classic one we saw in the past research. So with growth mixture modeling, we can actually look at different trajectories of groups of people across time. And when you add in predictor variables, then it becomes really interesting. Because then we would start to understand, well, what is it about these people that actually increase marital satisfaction across time? How are they different than these other groups? And our predictor variables can help us to better understand that. When we're looking at change in therapy, growth mixture modeling becomes very important. Because with this, we can understand what are the differences between clients who get better across time, those who don't, those who drop out, those who stay in. We can actually do some growth mixture modeling and add in some predictor variables and look at those different trajectories. And this is really where the most important research in our field needs to happen. When we are doing this kind of research, we can better answer our research questions with more sophistication, more accuracy, and actually get more accurate information back. So you're now at the end of the structural equation modeling class. So congratulations, you're now all SEM Padawans, and as you move forward, you can learn and become masters of SEM if you choose to do these analyses in publications and in your dissertations, and as you move forward in your career. This is really where the most important research of our field is happening, and if you look at any of the higher tier journals, you will find a lot of structural equation modeling in the quantitative research studies. So congratulations. You can move on now to do your readings for this week. Look at the example readings, cover any readings you haven't done, and then look at the concluding video where I wrap up the class.